Hello everybody. In this video, I'm going to go over Bay Area Math Olympiad 2013 problem number 5. This is another geometry problem. So let H be the orthocenter of an acute triangle ABC, and let A prime, B prime, C prime be the circumcenters of triangles BCH, ACH, and ABH. So these three triangles that are cut off. And we want to prove that the circumcenters, the triangle they make, is congruent to triangle ABC. So let's get a feel for this, right? And I'm not going to draw my full diagram, but when I worked on this problem, really in working on any geometry problem, if you draw a big diagram, then you will notice things, right? And the better the more capable you are of noticing things, the more likely you are to get the question correctly. So let's consider constructing one of these um, circumcenters. So it would be, I'm so off with this, but the circumcenter, right? To construct a circumcenter is to construct the perpendicular bisectors of each side. And that is because the perpendicular bisectors are the is the locus of points equidistant from two other of the 2 points, the 2 endpoints of the segment. And so if you intersect them, then they will be equidistant. Then they will be equidistant to all three, which is the definition of the circumcenter. So here I try my best. R is the midpoint of H and C. So I try my best to make it perpendicular, this line, but I know it's probably off. I can't even eyeball it. And we construct another perpendicular here. And so we get that the circumcenter is around here, right? And I'll use another color here. So we're going to call this is A prime. That was bad. So this is A prime. And so usually if you have congruence, right, then there's probably going to be a nice reflective argument. So we could see, like, if we drew lines from A prime to some other points, what, if could we get sort of a linearity? And so in fact, if, I'll do dark green for this, if you go from A to A prime, you see that even though my diagram was a bit eyebally, that goes through an N9 here. This is the 9-point center, which I talked about in my last video, on geometry at least. And so go watch that if you don't know what half this stuff is. And so it looks very obvious, right? We could claim that A prime, B prime, and C prime are all reflections, right? We're just taking the point B, or just taking a vertex and reflecting it across the 9-point center. So we want to show that this actually holds, that if I take this point and I reflect it over the 9-point center, I will get one of the vertices. So let's set out to prove that. That is now our claim. That is our goal. That if we reflect, and so that would mean that the whole triangle is just a reflection through the 9-point center, which means that they are congruent. So let's consider taking A prime and reflecting it, right? But what is A prime? A prime is the intersection of this perpendicular bisector and this perpendicular bisector, which means that wherever the two lines map, the intersection of those lines will be the map of A prime. So let's find out where the perpendicular bisector of BC goes, right? So L, where does L get mapped to? L gets mapped to this point T. And why is that? Well, if I draw in, okay, I have my ruler on. If I draw in this, right, we basically want to show that T and L both lie on this circle, and we want to show that they pass through the center of the circle. In other words, we want to show that this is a diameter. But I mentioned sort of at the end of my video last time that if you take a midpoint of one of the sides and the midpoint of sort of the vertex to orthocenter length across from it, then you'll get a diameter. The reason why is because here, this angle is 90 degrees. And if you have a 90-degree angle in a circle, that means you have a diameter. That is called Thales' theorem. So by Thales' theorem, we have a diameter here, which means that L maps to T. Now, we know that mapping is sort of angle preserving. In other words, the line that this perpendicular bisector BC maps to is parallel to it. But the perpendicular bisector of BC is obviously perpendicular to BC. So whatever it maps to is also perpendicular to BC. And now we see, and this is, I think, one of the foundational postulates of geometry, is that if you have a line and a point, there's a single line through that point, through the point that is parallel to that line. In other words, we know that this line right here is the map of this perpendicular bisector. So this goes to this. Now we want to know where this perpendicular bisector goes, the perpendicular bisector of CH, because wherever it maps, that will tell us information about where A prime maps. So again, we know that R, since R is a midpoint of CH, then we have another diameter here. So R is going to map to N. And again, we know that here we have this perpendicular bisector is perpendicular to CH. But CH is perpendicular to BC because it's an altitude. So in other words, since R maps to, wait, did I draw that in the wrong place? No, sorry. So since R maps to N, and since the perpendicular bisector of CH and the line AB are parallel, and since N is on AB, that means that the perpendicular bisector of CH maps to to AB. So now we know that A prime maps to the intersection of the line AH and the line AB. But that's obviously just A. It's right here. And that's it. That's actually all of the problem, is noticing that well, I mean, I guess the hardest part is noticing the reflection, which honestly you just have to draw a diagram, and it's a little, well, I guess I spent a little time on it, but just drawing a picture will will give you information, right? Because congruence, right? If you have a weird congruence, then you're probably going to have some sort of reflection, especially once you draw it. Just even if you have a vague notion of where A prime, B prime, and C prime will be, right? Because A prime is going to be somewhere over here across from A, and B prime is going to be somewhere over here across from B, and C prime is going to be somewhere over here across from C. So you have this triangle, so it's going to be sort of flipped through some point, is my best way of giving the intuition to this problem. But this is actually a complete proof, because this same argument goes for each of the circumcenters, right? They will all map, A prime maps to A, B prime maps to B, and C prime maps to C. which is enough to conclude that the two triangles are congruent. Thankfully, this is a short video, but a pretty difficult problem. Anyway, thank you for watching, and I will see you in the next one.